All right, let's take a look at plus minus calculating equilibrium concentrations, part B. Consider the reaction. If this reaction contains, I'm going to blow it up now that you know it's plus minus here so we can see it a little bit better. Consider the reaction. Consider the reaction. Carbon monoxide plus ammonia yields, wow, not even going to try that. Not an organic chemist. And there's the equilibrium constant. If the reaction vessel initially contains only carbon monoxide and ammonia at concentrations of 1 molar and 2 molar respectively, what will the concentration of the product be at equilibrium? So you can hear iced tea coming through loud and clear on you on this one. This is pretty much a straightforward where's my eraser? This is pretty much a straightforward ice chart equation, ice chart type of problem. So I'm going to come over here. I'm going to set up my ice chart. Okay, I like my new tablet here. The stylus is so much better. I don't know if you guys can see it showing up on your end, but my writing is a lot easier and I can get these nice small controlled movements that I couldn't with the other. All right, my initial amounts they gave me are 1.00 for my carbon monoxide and 2.00 for my ammonia, and nothing for my product. So my change has to be, notice they react in a 1-to-1 ratio. That makes life easy. Minus x plus x. So at equilibrium, my concentrations would be 1.00 minus x, 2.00 minus x, and x. So I'm going to set up my equilibrium constant. Uh-oh, Houston, we have a problem. If we look at our equilibrium constant, we can already tell without even trying that it's going to be too large for us to use our assumption. Our equilibrium constant is very large this time. So we're going to have to plug through and use that quadratic equation. Joys of joys. So let's get with it. We've got x equals 0.79 times thinking. So I'm going to go ahead and I'm going to do my foiling. Two minus 3x minus x squared gives me x equals 0.790 times 2. I'm distributing my 0.79, just so you know. 1.58 minus 0.790 times 3. That's 2.37x minus 0.1790x squared. Now I need to get it equal to 0, so I'm going to have to subtract x from both sides. I do that. I get 0 equals 1.58 minus 3.37x minus 0.790x squared. Crap, I just noticed something. Negative x times x should be positive x. So I need to go and change my signs for all that. There we go. Whoa, that would have cost us hours. All right, C, B, and there's your A. So now we're going to plug into our quadratic equation. It's the opposite of B, right? Plus minus B squared minus 4 AC divided by 2A so I've got 3.37 divided by, oh shoot, I keep making mistakes here. 0.790, which of course would be that 1.58. And that's going to be plus minus, calculator time, fun with calculators, 3.37 squared, come on, it helps if you turn them on, 3.37 squared minus 4 times 0.790 times 1.58, and I have an extra 0 there, I just noticed too, don't I? There we go. Notice I fixed that, yes? Just so no one gets confused. There was an extra 0 right there. So when I punch that number in, I get square root under the radical. I get 6.3641. I'm going to take the square root of that. That gives me 2.52 coming out. That gives me 2 possible answers. If I add, it gives me 3.7. And since I'm subtracting x, It can't be that large a number because that would create negative matter. So let's try the subtraction route. 3.37 minus 2.522. Divide by 1.58. That gives me a number that is less than 1, so I know it's not going to give me some negative matter when I subtract x. And that gives me 0.536 molar. So that would be my concentration of the unknown that they're looking for. And that's it.